All right, it looks like a few people are still waiting to get in. All right, that's fine. We'll wait a few minutes. And in the meantime, so what I did was I actually realized the syllabus does not actually mention the meeting times for this class. So I updated it. It's on Moodle, which I'm not sure if it's open here. You don't need to download it. I mean, all I did was add the dates, Monday through Thursday, 10 a.m. for our class meetings. That's it. But whoops, hold on a second. Here we go. But I just wanted to point it out to you because I realized, somebody mentioned it, that it doesn't actually mention when we're meeting. So this is the updated version. And this is right here. This line is literally the only thing I added to it. So you don't really need to bother looking at it again if you don't want to. But we do have one or two new people joining today. So I thought it'd be a good idea to add that information to the syllabus. Other than that, nothing's changed. And so today, what we're going to do is go right back to where we were yesterday, which is chapter 3. Specifically, we're going to revisit this concept of quantiles, which it's a fairly complicated idea, but there's it has some advantages that you don't get with some of these other measures. So let's see people are coming in. Very good. All right, so let's just wait one more minute before everybody gets here, and then we'll get started. So in the meantime, how's it going? Was there anybody scared off by yesterday? You're regretting being in this class? No, you're realizing how cool statistics really is. You're saying, wow, this is the best decision I've ever made, taking this class. Good. All right, that's what I want to hear. So, all right. Anyway, so we may as well start. Quantiles, they're used to divide a sample or population into equally sized groups based on their numerical values. By the way, I just want to remind you that we are now in the section of dispersion, where we're trying to look at not the center of the data, but how spread out the data are around the center. And I mentioned yesterday, this is important in finance because this will enable us to determine how risky a stock is, for example. As an investor, that's a huge deal. It's not enough to know how much, on average, the stock returns. We have to understand how much risk is involved. And one of the best ways to do that is to calculate a measure of dispersion for it. Typically, the standard deviation is what we see with stocks and other financial securities. But others also have. Okay. Oh. Anyway, let's get back to it. So quantiles, they're very useful for certain applications. In fact, all of these measures have strengths and weaknesses. I mean, there's no getting around it. No measure can be perfect. Otherwise, we would just use it all the time. So each one of these has its own advantages and disadvantages. It'll work well in some cases, not so much in others. And sometimes we have measures whose only purpose is to make things a little bit easier for us. For example, the range is very quick and easy to calculate. And sometimes that's all the information we really need. If we need to do a much more sophisticated analysis, then we may find ourselves tempted to try one of these more advanced versions. And so let's go back and visit. Now, we already saw that range is nothing but the difference between the largest and the smallest element in a set. Very simple, very straightforward. But what we want to do now is get back to the quantiles because they are kind of confusing. Specifically, in this class, we're interested in the quartiles. A lot of useful results can be obtained with quartiles. And so the term quantile can actually refer to any of these different kinds of systems for breaking down data into equal groups. I mentioned yesterday that percentiles are something you've probably seen before. The good thing about a percentile is that it lets you get a good idea of where a number is relative to all the others in a sample or a population. So especially with test scores, standardized test scores in particular, they tend to tell you two things. And you may recall this from your own SAT scores, which couldn't have been all that long ago. They would have most likely given you a raw score, which means the actual number of points you earned. And then they would have associated with that some kind of a percentile to give you a sense of where you stand compared to everybody else. Okay, because the raw score doesn't tell you a whole lot, does it? Like with the SAT, let's say the math section, it can go up to as high as 800. So if let's say you get a 700, you may say, well, 700 out of 800 doesn't sound that impressive. I mean, that's really only 87.5%. But what if it turns out that that's the best score in the country? Well, that's a very impressive achievement. So in other words, the raw scores by themselves often are not useful enough by themselves. The percentiles are what's really going to help us understand where we stand compared to everybody else. Sometimes you see deciles. This means you don't need quite so precise information. Like, for example, the 8th decile means you've done better than 80% and worse than 20%. But you don't see that used a whole lot. But what you do see quite frequently is these so-called quartiles, where we're literally taking the data and breaking it up into 4 pieces. Sometimes that's all the information that we really need. So the way it works, and I'll mention this again with a little graph or chart, is we're breaking it up into 4 pieces. So imagine that you have your minimum score. Here's your maximum. And then what we're trying to capture is groups of 25%. Okay, so this represents 25%. This is actually another 25%. So you can see that 25% represent each of these groups. But the key detail here is that the total up to that point is 25, 50, 75, and of course 100 for the maximum. Okay, and so if you were told that your score on an exam is in the 2nd quartile, that means you did better than half the class and you did worse than half the class. All right, that's basically how to look at it. Now, what we're trying to do is calculate the actual values of these quartiles. Now, that's proven to be a bit challenging because it's a 2-step process. First of all, we have to identify what's called an index or a position within the sorted data. And then we have to figure out what number we're actually looking for. So we have these positions, which we need to remember for calculating our quartiles. Okay, so in other words, no matter how much data we actually have, let's say, for example, we have the number, oh, wait a minute. I got some messages here. Are quantiles always even? That's a good question. I'm going to say probably makes the most sense. I mean, I wouldn't want to break up my data into 3 equal pieces, or maybe 5 might be okay, but I think it just makes intuitive sense to people to break it up into even numbers. Remember, these measures are meant to be useful and helpful to people to help understand the properties of their data. So it stands to reason that the measures we develop would be based on ideas that people really understand. Like, for example, 10. Everybody gets 10. 10 is at the heart and soul of almost all the calculations that we do. Base 10 is, really everything we do really ultimately is based on base 10. And some people have theorized that the reason why 10 makes so much sense to everybody is because literally we have 10 fingers and we can count on them. And so this is apparently how this number system got started. We could have just as easily wound up with base 7 or 13 or 19 or anything, but 10 is something that makes sense to everybody, so we tend to see it used. But other numbers work as well, like 4 quarters. Everybody understands 4 quarters. If you ever notice that financial data tends to be reported every quarter, which means every 3 months, because somehow it just makes sense to people to do something 4 times a year. Or with percentiles, we saw that that's actually 100, which is another number that makes sense to everybody. And so that's why these quantiles tend to be based on even numbers. It's just all about what makes intuitive sense. All right, anyway, which by the way reminds me, I remember one year I was teaching at another school, and it was time for the evaluations at the end of the year. And I discovered to my great surprise that for each of the questions, you were supposed to rank the professor on a scale from 1 to 9. I couldn't believe it. 9. I'd never seen that before. Why 9? Why not 10? That's what everybody likes, is 10. So, you do see that very occasionally, but usually we end up with these even numbers. The only exception I can think of is 5. Sometimes people like to break up data into sections of 1/5 each, or 20%, but basically quantiles are typically based on even numbers. Yes. All right, let's get back into this. So these are the positions. Now this represents the element that you're looking for. So let's say we had 1, 3, 4, 6, 9, 10, 1, 2, 3, and 15. Okay, so you got 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. So the quartile, for the first quartile, you're looking for number 2.25. Now that's very unfortunate because there is no 2.25th element. That's going to come somewhere in here. Somewhere between 2, 3, and 4 is our first quartile. Now the second one, 2 times 8 plus 1 over 4. So the position of the first quartile is 2.25. The second one is just double that, which is 4.5. Halfway in between the fourth and the fifth element. Okay, and then the third position would be 3 times 8 plus 1 over 4, which is 6.75. Somewhere between here. Now we know that there's no 2.25 element, there's no 4.5 element, there's no 6.75, but what we can do is use a process called interpolation, which basically means we're going to find that distance, which puts us at, in this case, 75% of the distance between element numbers 6 and 7. This one would put us halfway between elements 4 and 5. And this one will put us 25% of the distance between elements 2 and 3. Now, the interpolation process itself isn't really all that complicated. It just takes a little getting used to. So, you know, let's run with this example for a minute. And so let's try this. Let's actually calculate them with our interpolation technique, okay? So let me just copy these down again. I've got 1, 3, 4, 6, 9, 10, 12, 15. Now, the first quartile is in the position 2.25. So what exactly is happening here? Here's 3 and here's 4. I'm looking for a point that's 25% of the distance between these two. So in other words, this mysterious Q1 is 25% of the distance between 3 and 4. So what number would I associate with that? Well, the way you do that is start with your 3, and then you add 25% of the difference between these two. Now, when they're only 1 apart, that makes things pretty easy. So in other words, we're going to define 3.25 as the first quartile because it's in the right position. In other words, now, of course, you notice that we're making an assumption here. And this is where it gets controversial. This is why not everybody does it this way. We're essentially assuming that these numbers are spread out in such a way that this needs to be, that there's some kind of linear relationship here, which may not exist. So we're assuming that if you were told, let's say that these are 2 addresses on the street, and let's say the guy's going to come and read your water meter, and let's say it's located out in the yard somewhere, and the guy's told, listen, it's 25% of the distance between the left fence and the right fence. Well, then he would know how to find it by using a technique like this. Now, the second quartile is easy because it is nothing but, wow, that was scary. it's really nothing but the median. In other words, for this one, if you choose to do so, you can replace this interpolation business with the median if you want to. But look at what you're doing here. You're trying to find the exact middle of this interval. 50% is on either side of this Q2. Now, I think you can see for yourselves that it's going to end up being 7.5. But how is that? Because it's 6 plus half of the difference right here between 6 and 9. So it's 6 plus a half of 3, and that's 7.5. 7.5. I was right the first time. Now, if you applied our technique for the median, remember you were told that you would take the average of the two in the middle, 6 plus 9 over 2. What do you know? It's the same thing. So this is basically a double check. Because remember, the median and the second quartile are the same thing. And then number 3, 6.75. Somewhere in here. Oh, look, no, you know what? Let me just do this. I want to change this to the actual values rather than the positions so that you can see later on what's going on. If I leave it at 4.5, that was actually a position. Let's keep these all at the actual values. So this one, if you recall, the position was 6.75. I'll tell you what, let's write that underneath here. And this first one was 225. All right, that way you can distinguish between the actual quartile and the position. Now, in this last case, we're somewhere between 10 and 12, but we're 75% of the way between the two. So how do we find that? We start with the 10. We always start with the lower number, and then this percentage determines what comes next. And then this last value in the parentheses is just the difference between the two endpoints. And that ends up being 11.5. All right, so I'm hoping that by visually seeing these pictures, it's easier to figure out what exactly is going on here. Yes, it's a bit of a pain, but it's certainly not, once you get used to it, and it's just like anything else, you practice. But as long as you conceptually understand what we've done, you should never have a problem with this. Now, of course, you might get lucky. I mean, it's possible that your position will be an integer and then you're all set. Let's try another one where that actually happens to be the case. Let's say that your data are 1, 3, 4, 5, 6, 8, and 10. Okay, so now the Q1 position is n plus 1 over 4. Oh, look what happened here. We got an integer. So this is Q1. Man, it's nice when things work out like this, isn't it? But it's so rare in the real world, that things usually don't work out nicely. That's unusual. The more normal case is for things to work out not nicely. Okay. All right, so you plug these in. And, okay, so in other words, the Q1 position is 2, but the actual value of Q1 is 3. Q2's position is 4, which means that Q2 is equal to 5. And Q3 is positioned as 6, which means that its actual value is 8. So I'll just summarize that here. Q1 is 3, Q2 is 5, and Q3 is 8. All right, so in that case, you got lucky. Now, I just want to point out too here that we're looking at very small samples here. If you had a large enough amount of data, all the other techniques that are out there for finding quartiles would probably give you very similar results to what we did here. It's only when you have very small amounts of data that there can be big differences between the different available techniques. All right, so yesterday we looked at this, so we don't need to go through this all over again. We've already done this one. The steps, it goes through the steps. What I wanted to do is show you this next idea, the so-called interquartile range, which you can see is very simple. It's just the difference between Q3 and Q1. So remember, here's our diagram. And basically what it represents is the middle 50%. Okay, now I didn't put this in the slides. I'd like to introduce it here now, just as a quick example of what we can do with the interquartile range. A very good example is this. We can define an outlier in the following way. Now, remember, we mentioned outliers before. It's a very large or very small number, but it's sometimes hard to be sure what is an outlier. In other words, sometimes there are cases where a number might be an outlier, might not be. So we need a formal test to determine if a number is in fact an outlier. So here's one way that is often used in practice. Okay, a number is an outlier if it is, okay, greater than, Q3 plus 1.5 times the IQR or less than Q1 minus 1.5 times the IQR. Okay, so in other words, you can actually formally test whether a number is an outlier by checking to see if it falls into one of these two categories. So there you go, an application of the IQR, which is very helpful because then you can say, yes, this is an outlier. No, it's not. Okay, so you've got a specific range of values that you can say, okay, this is what we mean by an outlier. And it's very helpful as opposed to saying, well, you know, it looks kind of big compared to the other numbers. That's very awkward. In statistics, we need to have a formal test for everything that we try to claim. In other words, if you try to claim that a number is an outlier, you have to be prepared to back it up with a formal test. So statistics is heavily based on testing ideas, formal tests to determine if what we think about our data is true or false. So we'll see a lot of that as we go along. So, and of course, you know that statistics is a huge, huge area and it overlaps with a lot of disciplines, but it is a study, I mean, it is a discipline all of its own. In fact, you can actually, in a larger school, you could actually major in statistics, even in the college level, because it's such a deep area of study. So you never know where you might be heading in the future. That could be you one of these days. All right, anyway, so, oh, one more thing. These should be subscripts. Let me just fix that. Whoops, no. There's no point in leaving errors in here when I can fix them. Look how cool that is. Font subscript. You're getting PowerPoint lessons as we go along here. Okay, so this is just, oh, you know what I'd like to do too? Let's make this really fancy. Ooh. Now, by the way, yesterday after we were done, I posted the version of the slides that I was working on yesterday. So all the handwritten notes are actually in If you go to Moodle right now, you'll see it's there. In fact, let me show it to you. And then when we're done today, I'll do the same thing. You see, it says chapter three with notes. That's all of yesterday's handwritten notes. Today, it will contain all of these. So you'll have 2 of them. All right, good. Now we're ready for the really important measures of dispersion. It's, you know, the interquartile range, the quartiles, the range, they're important too, but by far the most widely used measures of dispersion are these 2, the variance and the standard deviation. Now, as it turns out, these are not 2 separate concepts. And we'll get to this in a few minutes, but the standard deviation itself is nothing but the square root of the variance. So once you've got your variance, it's easy to calculate the standard deviation. Easy. Now, we'll see why in a few minutes you might be tempted to do that. But first, we have to define the variance. Now, here, we're going to have a separate formula for, oh, by the way, if you've noticed, it's been a while since we had a formula. The range is just a procedure. The quantiles, rather, are just a procedure. But variance and standard deviation have actual formulas again. And we need to do one each for samples and populations. So we're going to start next with the sample variance. And when you see it, you're going to recognize that way back here, we went out of our way to really understand the summation operator. Specifically, this case, and you're going to see in about a minute why this turned out to be so important. Okay, let's check this out. All right. Uh-oh. Need some muting. Yeah, sometimes people sign in without realizing their microphones are on. And, oh, you don't know what's going to happen then. So, all right, let's get back to this. So the formula, you'll recognize right away what I'm talking about here. Oh, that should ring a bell. Now, just remember, though, that X bar is a constant. So what you're seeing here is just our old friend. Oh, yeah. Remember that from all the way yesterday, 24 hours ago? Yes, you do. And what is this telling us to do? You're taking each element in your sample, you're subtracting this constant, you're squaring the results and adding them up. And that's exactly what you're doing here, except that now the constant itself is the sample mean. So what you're basically trying to do is find out how far on average your elements are from the center. How spread out are they? So then in the denominator, you can see you're dividing by n-1. Now, here, this symbol represents the sample variance. And if you notice, of course, S is a Roman letter. We're using that to represent the sample variance. So now we're going to do one of these. This is the same example we've had before. And you'll recall that we've already figured out that for this case, the sample mean is 2. So that part is done. So now what we're going to do, and by the way, for this, you don't need to do any sorting. You can, but it's not necessary. So you're going to go through each one of these. Here's what you have to do. Now take a look at this. What exactly is going on here? You've got all 5 elements in your sample, and in each case, we're subtracting the sample mean of 2 before we square the result. Okay, so what exactly is happening here? This is x1. This is x bar. This is x2. This is x bar. x3, x bar. I might as well add the minus signs. And of course, we must square them. And then, only then, we can add them up.
I just have a quick question.
Sure, go ahead.
So what if we decided to make the numbers into a numerical like order? Like if we decided to organize the numbers, would it change our answer?
It would not, no.
Just out of
Like,
curiosity.
yeah, if you feel like you want to sort them, in fact, you could try that as an experiment. Just sort them out and you'll see that you'll get the exact same number.
Thank you.
Now, later on, we're going to see a type of calculation where the order does matter though. So, but for here, it does not matter. All right. And then of course here, the reason why this is 4 is because remember the sample size was 5. All right. Now, what we'll do next is actually evaluate these. Now, what probably you should do, this is my opinion, is rather than try to do this directly, just to avoid mistakes, which are so easy to make in this case, first evaluate what's going on inside the parentheses and then square them. This is the kind of formula where it's just so easy to make mistakes. It really is. And so now it should be more clear what you're doing, and that's going to make it much harder to make mistakes. So you can see that, for example, you'll have 0, 9, 1, 9, and 1. And whatever that adds up to is what we're looking for. All right, let's go into the next slide, and you'll see that that results in a variance of 5. Okay. Now, this is an important measure. Now, there's one big problem with the variance, though. Remember, we decided that, let's say that these numbers represented temperatures. The problem with the variance is that because of the way it's defined, the units are squared. So in other words, this is actually going to be 5 degrees squared, which makes no sense to anybody. So what are we supposed to do? 5 degrees squared is what is that? We don't know what a degree squared is. So this is why we need the standard deviation. The standard deviation takes this number and basically takes the square root to get rid of this problem with the units. So when you look at the formula, you'll see that all we've done is taking the square root of the variance. It's literally the square root of s squared. And here, the reason why we do this eliminates the problem of squared units. Whoops. Okay, so when you do that here, of course, you're going to wind up with the square root of 5, which is approximately 2.236 degrees. So it's the same units as the underlying data. And so this is why the standard deviation is typically used as, most widely, I would say, as the measure of dispersion of choice. Most people use this to represent the dispersion in their data. The variance has its place, but for actually understanding what's happening here, this is the way to go. Now, by the way, here's a fun little side note. You probably are wondering now, well, then why did we square this in the first place? Why don't we just add them up the way they are? Isn't this causing problems? And the answer is yes, but here's the issue. If you left off the square here, no matter what numbers you have in this equation, it'll always add up to 0. So therefore, it becomes a useless measure. We have to square the results in order to come up with a meaningful measure. The other option is to do the absolute value, but that apparently has some very awkward properties. So this is the measure of choice. We square the results with the understanding that when we're done, we'll have to take the square root. Okay, now the population has its own formula, although in this case, there's more differences than just the notation. You'll see what I mean in a second. So this is the equivalent formula for the population variance. So there's really three differences. Number one, we've got this letter. Now, here's an interesting fun fact. This letter is the Greek letter sigma. Well, how is this possible? Isn't this also the Greek letter sigma? Why, yes, it is. And how is this happening? Because this is the uppercase version, and this is the lowercase. Just like we've got these two letters in the Roman alphabet, they're both A, but one is upper and one is lower. The same thing happens in the Greek alphabet. In fact, I've actually asked this question of some of my classes. When we have people in the class who speak languages that are not Western European languages, I always ask them if they have case in their languages, and they always say no. This is apparently unique to Western languages. So I guess, you know, for whatever reason, the Greeks and the Romans used case, but other cultures like Japanese, for example, or Chinese, they don't have this concept in their language. So anyway, the differences here are sigma squared is now the population variance. So once again, we're using that rule that Greek letters are used to represent a variance. The square tells me that it's a variance. Then here we've got mu, the population mean again, instead of x bar. And of course we have n, which is our population size. What else do you notice that's different? Let's see, I'm going to test our powers of observation right now. What else is different besides the letters? Is there one other difference here, maybe in the way it's calculated?
We don't subtract one from the
Yes, exactly. With the sample version, we're dividing by n minus 1, and here it's n. Now, that may seem like a subtle difference, and it is, but it's important. The reasoning behind this is so horrifically complicated that I usually recommend that people just take my word for it. But I do have an article here somewhere on my hard drive that I can send you if you really are dying to know why this is happening. But I have to tell you, if you read that article, you may decide, you know what, it's okay. I'll just believe it, because it's a very complicated set of reasons. So you decide. If you really are saying to yourself, I've got to know the mystery of why this is happening, just ask me, send me an email. I'll send you a copy of the article, but I'm not so sure that it'll mean anything to you at this level. So anyway, but this is something. Now, the reason this is important is because when you have, let's say, a problem set or an exam, it'll tell you in the problem if the data you're being given represents a sample or a population. So you have to make sure that you know which one it is before you start doing any calculations, because in a case like this, for example, if you're not sure, you're bound to get it wrong. So this is one of the reasons why it starts to really matter if you have a sample or a population for your data set. Now, fortunately, the relationship between the variance and standard deviation is the same for samples and populations. In other words, the population standard deviation is literally just the square root of what you're seeing here. That part never changes, okay? That relationship is always the same. In other words, no matter what kind of data you're looking at, the standard deviation always equals the square root of the variance. And again, it's for the same reasoning. We have to be careful with our units. The variance gives us squared units, which is not doing us any good. All right, so, man, this is only day 2 and we're really zooming along here, aren't we? Yes, we are. But you know what the thing is, there's something to be said for having a class like this so soon after the semester ends, because you're still kind of in that school frame of mind, aren't you? you're used to studying. You haven't lost the good habits yet of studying. By the time it gets to be the end of January, yeah, it'll start to get a little slippery there. But right now, we're still in that school mode. And so everything works for you, doesn't it? Yes, it does. All right. Now, the last measure that we want to look at is the so-called coefficient of variation. And luckily for us, it is simply based on existing measures that we already know. This is a little bit different. We're trying to capture two things at once in a coefficient of variation. We're looking at the average value of the elements in a sample, and we're also looking at how spread out they are. So we think of this as a measure of relative dispersion because it is not the others, you could think of them as an absolute measure of dispersion. This is what we will call a relative measure because we're trying to capture how much spread there is in the data as a function of the actual mean itself. So in other words, it sounds very mysterious, but what this is all about is that what you're doing is taking your standard deviation and dividing by the mean, and then usually we multiply that by 100 to turn it into a percent. So this applies to both populations and standard deviations. Of course, samples. So that, for example, the sample coefficient of variation would be written as S over X bar times 100. The population version is going to equal sigma over mu times 100. Either way, it's the exact same logic. Now, for certain applications, this is actually a better choice than either the mean or the standard deviation by itself. Yeah, and I'm going to show you one in a minute. Okay, so this is how this thing is defined. So what we're going to do is apply this to stocks. Now, with a stock, the point of owning a share of stock is that you want the returns to be as high as possible, but you also want to minimize your risk. So in general, you can't really have it both ways. Usually the stocks with the highest rates of return are also the riskiest ones. So what you have to do is find the one that makes the most sense for your particular circumstances. So the best way to compare these stocks to each other is with this particular measure, because then we're taking into account both the risk and the return, where the risk can be thought of as this standard deviation. So let's look at this example. Okay, they're actually portfolios. Okay, stock portfolio A and portfolio B. We're going to think of these as populations. So portfolio A, the mean or average rate of return is 8% per year, and the standard deviation is 16% per year. Okay, so on average, if you hold this portfolio year in, year out, you'll make 8%, but there's going to be some variation from one year to the next. Okay, in other words, the value doesn't have to go up 8% every year. Some years it'll go up more than that. Some years it'll go up less than that, but it'll average out to about 8%. This tells me how much it can change from one year to the next. So let me just show you like a quick example. When we're done, I'll show you a quick drawing. Now for B, the mean is a little higher, if you notice, 10%, but the risk is also quite a bit higher. And that's what you normally expect. Okay, so just as a quick aside, imagine you do have two stocks or portfolios to choose from. And this would be the value, the price. And this is time. So here's a stock. These aren't necessarily the same ones we were just looking at. In fact, let me call this stock X and stock Y. So stock X is very, very stable. The price hardly ever changes. So on average, now if you notice, the price is rising. So the return is low. But you also don't see these enormous fluctuations. You also have a low level of risk. Whereas here, look at that one. The prices are bouncing around all over the place, but look how rapidly it's growing. Okay, in other words, if I were to define a trend line through here, it's very steep. Over here, if I do that, it would be very flat. Let's see if I can do that properly. Very flat. So that means this one on the right has a high return, but high risk. And again, you can tell how quickly it's growing, but look how steep that line is. The price is going up pretty quickly, but there's all this bouncing around. So from one year to the next, you don't know what's actually going to happen. This one is extremely predictable. Let me just write that a little neater. And so you have to pick the one that makes sense for you. Now, if you really hate risk, you might want to buy the one on the left. Let's say you're already retired and you don't really want to take on a lot of risk. You might buy StockX. If you're young and you've got plenty of time to recover from losses, you might buy Stock Y because it's, the potential, the upside potential is higher. So the risk here, now remember the risk can be measured by standard deviation. So then let's go back and revisit stocks, these two. So remember A, 8%, 16% is the risk. For B, 10% is the return, but 30% is the risk. So in other words, these more or less correspond to what these two graphs look like, although these are a little bit more exaggerated. Here's what we're going to do. Let's calculate this coefficient of variation for A and B. So for stock portfolio A, the ratio of risk to return is 200%. For B, it's 300%. Now, let's ask ourselves this question. In a case like this, do you want this number to be high or low? What do you think? In fact, you know what, maybe, this is an excuse to do a poll. I like that. Should we, or which is better? A high coefficient of variation or a low coefficient of variation? Oh, wait, I keep forgetting. That's just the title. That's right. So the answers are going to be high and low. Let's see what we can come up with. All right. And hopefully it'll work better than it did yesterday. Okay, did I forget to mention there's a prize? No, there's no prize. All right, I guess everybody has got their opinion out there. So the answer is low. You're absolutely right. The low people, the high people, let's take a look and see why. Okay. Yeah, because remember, standard deviation is the risk. Mean is the return. So you want that risk to be low as possible relative to the mean. So you can see, even though B promises a higher potential return, it's quite a bit riskier relative to its return. And so you probably would be better off with A. Not that you can't buy B, but I mean, most people would choose A because the amount of risk compared to the return is quite a bit lower, as a matter of fact. So this is one other way you can use to determine, just as in our example, which stocks you should buy. This is the example. I picked this one because this is the one you're most likely to encounter in your actual life. Like, for example, in 10 years, when you're working and earning a lot of money and you're looking around for investments, these are exactly the kinds of things you'll ask yourself. What stock should I buy? How do I make these decisions? Well, one of the ways you can do that is by looking at this coefficient of variation measure. Okay, so now we're getting to some really, if you thought what we were doing before was deep and intense, now we're getting, it's like we've been swimming in sort of the shallow end of the pool, and now we're ready to dive into the deep end. We're going to introduce what are called measures of association, where for the first time, we're actually comparing two different samples or two different populations. Yeah, and so unfortunately, the formulas are getting even messier as we reach this point. So don't despair, though. In the next chapter, what we'll be studying will be more theoretical and less computational. So notice not all the chapters are going to require quite so much calculation. But here we do. We have to grind out all these numbers. And what we're trying to determine here is whether or not two variables tend to move in the same direction. And the two measures that we'll use are covariance and correlation. Between the two, it'll turn out that this is the more useful one. And you'll see why when we get there. So why don't we stop and think about this for a second? What does this mean for two variables to move in the same direction? For example, let's try this one. Well, let's do a poll. What the heck? As long as it's here. Now, last time I was having trouble with this. I don't remember how. I want another question. All right, here we go. Would you expect that a corporation's sales and its profits would tend to rise and fall or fall during the same years? All right, let's try this one. Oh, this is so much fun. Oh, where did it go? Oh, that's interesting. Well, this one is still sitting here. Well, this is really bad. I don't understand what they're thinking of here. Does anybody see any obvious way to stop this one and do a new one? I mean, this is what's so typical for me in technology. I mean, they obviously think that these instructions are there's no instructions. They think this whole thing is so self-explanatory, but what the hell, you know? What am I supposed to do here? I typed it in. So you stop this one. I tried to create a new one and it just disappears on me. Well, let's try that again. Would you expect that a corporation's sales and profits would tend to both increase or decrease, let's put it that way, during the same year? Let's see if it will actually let me do this now. Well, so much for that. And we're back to this crap again. Oh, I see. So very helpfully, they did not mention that there's a menu here. God. All right, let's try it. Okay, well, I don't think there's any need to ask this question. I think it's pretty clear that during years when their sales go up, their profits will have to go up too. I mean, how could they not? But in years in which the sales fall, their profits would tend to fall too. Oh no, we have somebody who said no. No, that can't be right. That's how their profits come from, ultimately, is their sales. But anyway, how about this one? Let's see if it'll let me do another one. How about correlation 2? What would happen let's say, what would be the relationship between a corporation's profits and its costs of production? Ooh, they tend to increase or decrease at the same time, or during the same year, I guess. And they tend to move in opposite directions during the same year. All right, I guess it will maybe allow me to do that. Here we go. I didn't have a third choice. I'm not sure. You have to pick one or the other. All right. Well, it turns out, all right, when we're done, I'll tell you. I don't want to spoil it. What happens when the cost of production, let's say, for example, that this is a company that makes jewelry, and all of a sudden there's a huge increase in the cost of gold. What would tend to happen to their profits? Most likely that'll eat into their profits because it costs them more money to make the jewelry. So what we're getting at here is this idea that for some variables, tend to move in the same direction, while others tend to move in opposite directions. Okay, there are many variables that are unrelated to each other. So we've really got three possibilities here. Variables that tend to move in the same direction, variables that tend to move in opposite directions, and variables that are really not related to each other at all. So we want to quantify this relationship between them. We want to not only understand the direction, but the strength of that relationship. Okay, and that's what these measures will enable us to do, to capture the strength and the direction. So what we're going to do is this. I'm going to make up some examples right now, but I'm going to do them in Microsoft Excel. I'll tell you why, because I want you to see its wonderful graphics capabilities. And so let's say we have some corporation. Let's say we have 10 years worth of data. Okay, so here's sales in millions. Means millions. All right, so I'm just going to, of course, make up these numbers right now. All right, so what I'm going to do is show you this very cool graph, which you may have seen before. Let's see now. Let me just make it readable for you. I see they have it backwards here. Hold on one second. I have to make one little change here. And then I want to make it look a little nicer. So I'm going to tidy it up a bit. Okay, so what I've done here is created something called a scatter plot. And what I've got here is on the vertical axis is, oh, wait a minute. I think they were right the first time. Hold on a second. Oh no, did I waste all that time? Oh, I blew it. No, it was right the first time. All right, hold on. Let me fix it. Oh, Jesus, I've really screwed this thing up. Hold on. Let me start it all over again. All right, okay, that's got to be it. Okay, we're good. All right, I'm just going to tidy it up one more time. And on this side, okay, now it looks pretty good, I think. So this is a scatter plot, what we call a scatter plot. And so what I'm going to do is label this. These are the cells. And then over here, we're going to have the profits. Oh, no, up here. Okay, so what is it that jumps off this screen at you? What is it? What do you notice about these points? Now, each one of these points represents a single observation. For example, this one, in fact, let me put the data labels in here so you can see. No, that's not what I wanted. But this one, for example, represents, it looks like that would be this first year. And so each of these points is a single year worth of sales and profits. But if you notice, if you look at the points, they have a tendency to both increase together. In other words, this is the x-axis. Sales, let's put that in the label there. When sales are increasing, there's a very strong tendency for the profits to increase as well. Not always, and not always by the same amount, but there's a very strong tendency for both of them to rise at the same time. And we can visually see this with our scatter plot. And in fact, you can add what's called a trend line here. As you can see, the slope of this line is positive. And that tells me that the two variables tend to rise together. And this is what I'm looking for. I want to find out if they tend to rise or fall together. And then the next step is to find out how strong this relationship is. Because you can see the points are not all directly on this line. So that means something else besides sales is driving these profits. But the relationship looks very, very close. So what I would like to be able to do is use the covariance and correlation measures to tell me how strong this connection is. Okay. Now I'd like to do the same thing for two variables that move in opposite directions, and then we'll have another case where they are essentially unrelated to each other. But unfortunately, we've reached break time, so we'll have to wait a few minutes to see these results, and I'm sure you're excited about it. But let's knock it off like we did yesterday for about 10 minutes or so, and then we will come back and I will show you the other two types of graphs that could result from this, and then we'll dive into the calculations. All right. But the most important thing is to make sure you understand what these measures are telling us. That's why I'm going through all these steps. And I will put these in Moodle, by the way. If you want to take these home and look at them, you may already have some Excel skills. If not, you really should start working on them. And this way, it'll give you an opportunity to start to learn some of Excel's capabilities. All right. So why don't we stop for a few minutes and then we'll come right back and pick it up with some more wonderful plots. And then we'll do the calculations, okay? All right. Well, now we know the weather. All right. Oh, by the way, couple of things. I'm supposed to find out if anybody is not actually attending the class. So I'm just going to make a copy of this. Yeah, in the beginning of any course, you never know who's going to actually show up. Hold on one second. They don't make this easy. Okay, that should take care of that. Now, the other thing too is that the chapter 3 problem set is on Moodle, but we're not done with chapter 3 yet, of course. And it's Christmas time, so it won't be due till, probably not even when we get back next week, but maybe later on that week. So next week, we're going to have the normal Monday through Thursday. So, don't worry about the chapter 3 problem set just yet. Probably we can hang on to that until sometime late next week. I don't want people to be doing homework on Christmas Day, that's for sure. But yes, at some point we'll have to, of course, do all those problem sets, but that one can probably wait till let's say next Wednesday or Thursday. All right, so let's get back to it. Now, we need an example where the variables are going in opposite directions. So let's do that. Just so you can see how it's different. So let's try, like I said before, cost of production. Oh, actually, I did this wrong. This should have been on this side instead of sales. This is still profits. We'll keep the same profits, but I'll change the cost of production. Okay, so let's see, what can we do here? So this would be like labor and raw materials and things like that. Let's see, 50. All right, let's see what this looks like. All right, so this is our scatter plot. Anyway, so let's label this. These are cost of production. Let me just double check this. Yeah, that's fine. All right, so we're just going to put some labels on here. The horizontal axis is cost of production instead of sales. X and Y over here will be profits, just like before. So, and I'll just clean it up a little bit here. All right, that's better. And I'll add a trend line so you can see that the slope is negative. All right, so in other words, what is this proving? it shows that when the costs of production go up, the profits tend to go down and vice versa, which makes perfect sense, of course. Here we had the other way around. So here, the relationship between the two variables is positive. Let me make one more little change here. That's better. Okay, so here it goes the opposite direction. And then we need a third case where we have two variables that are completely unrelated to each other. And that could be, let's say, the temperature. Oh, not there. The temperature. There's no reason why our profit should have anything to do with the temperature. So let's make, this will be a nonsensical relationship. It doesn't exist. Let's just see what we can do here. Okay, I hope I've chosen them wisely. Let's see what this thing looks like. Okay, so the idea here is it's supposed to look sort of randomly scattered around. Let's see. All right, that's not too bad. Let's put in a trend line. It should be more or less flat. Yeah, that's good. Okay, and so once again, this is scatter plot. The horizontal axis is temperature. And then on the vertical axis, we'll have, oh, no, we do that from here, the profits. Okay, so we got the three possible cases. We have a positive relationship here between profits and sales. We have a negative relationship between cost of production and profits. And then finally, we have essentially no relationship between temperature and profits. So now you can see that visually from these scatter plots, but what we'd like to be able to do is quantify this information by using either the covariance or the correlation. Now, what I'm going to do here, just to speed things up a little, first, I'm going to actually calculate these measures in Excel, and then we're going to take a step back and see where they came from. Okay, so let me just do this real fast, and then we'll explain what these numbers actually mean. Okay, hold on. So we'll do the covariance first, and then we'll do the correlation. Oh no, oh, I spelled it wrong. Now it's happy. All right. All right, so you can see now, right now, I just want to point out that here, you notice how both of them are positive, which is what you would expect because the slope of this trend line is positive. That means there's a direct connection between the two variables. There's a strong tendency for them to both go up or down at the same time. But down here, they're both negative. And again, that makes sense because the fact that this trend line has a negative slope comes about from the fact that when we have higher cost of production, we have lower profits and vice versa. And then down here, although it's not perfect, these should be very close to zero. Okay, they're slightly negative, but it's very, very close to zero. Zero would mean that there's absolutely no connection there whatsoever. This connection here is probably a coincidence because these numbers are completely random. But these should be very, very close to zero, which they are. All right, so those are the three possibilities. And then most cases fall somewhere in between. Let me quickly save this before I lose it. Oh, we're going to find that out in a couple of minutes. What does it convey? Yes, that's where we're headed next. Okay, so yeah, the graphs are fun, but we want to understand what these numbers are actually saying to us. Okay, so let's hold on. What's the winter? So I'll be putting this up. Now, I've seen books that explain it this way. Let's see what I can do. In terms of, let's say, graphics, imagine this graph being broken up into quadrants. This is the first quadrant, which means X and Y are both positive. This is the third quadrant down here where X and Y are both negative. So the idea here is that most of these points are either in the first quadrant or in the third quadrant. What does that mean? Either there's a very strong tendency for them both to be positive or both negative at the same time. So when you see something like this happening, the majority of the points are either in the first or third quadrant. This is what it means to have a positive covariance or correlation. When they're above their own average or below their own average, it tends to happen at the same time. Whereas with this one, it would be the other way around. In other words, if I drew these lines now, this is the second quadrant, and this is the fourth quadrant. In the second quadrant, Y is positive and X is negative. Down here in the fourth quadrant, it's the other way around. Okay, Y is negative and X is positive. So what that means is most of the points are in the second or the fourth quadrant, which means they tend to have the opposite sign, which means they tend to move in opposite directions. And then in the last case, what we would expect to find is more or less an equal balance between the quadrants. One, two, three, and four. And that's pretty much what we have here. It's not perfect, but you notice instead of, unlike above, where we have clusterings in the two quadrants, here there's a random scattering between all four quadrants, which suggests that there's no particular relationship between X and Y. Did that make any sense? I hope so. That's part of the way to visualize what covariance and correlation are telling us. Okay, so here we have a positive correlation and covariance because the points are mostly in the first and third quadrant. Here, it's the other way around. These are negative because most of the points are in the second and the fourth quadrants. And here, this is close to zero because they're just randomly scattered all over the place. All right, now it's time to look at the actual calculations. Now, this is what I've been dreading because when you see the formulas, you might pass out. No, you might not pass out, but you might feel like it. But don't worry, they're not as brutally complicated as they look. We just have to get used to what they're actually telling us. Now, the first one we have to note here is that unlike with the previous measures, here we're looking at either two populations or two samples. So naturally enough, the formulas will be more complicated. So what does this look like? Let's jump ahead. Here's the sample covariance. Now, keep in mind, you notice how there are X's and Y's in here. Why is that? Because we have a sample, which we'll call X, which has a mean of X bar, and each element is labeled as Xi. And then we also have sample Y. Same thing. Each element in sample Y is labeled Y sub I, and it has a mean, which we'll call Y bar. Now, this part hasn't changed. This is the common sample size. By the way, this is something I forgot to mention. You must have the same number of elements in both samples in order to calculate the covariance and the correlation. So we'll call this the common sample size. And you notice this new notation. Since this is a sample, we'll use the Roman letter S. The two subscripts are there to remind us that this is actually a covariance. Okay, so you don't get it confused with the sample standard deviation. We have two subscripts. That's meant to be the reminder that this is covariance. Now, what's going on here? For each X, you're subtracting the mean. For each Y, you're subtracting the mean, and you're multiplying these terms together, and then at the end, you add them up. So we'll get an example going in about a second. So this is your sample covariance. Now, it is a very messy process. There's no getting around it. All right, now let's see. I'm looking to see if there's any scared faces. No, everybody looks pretty calm. Okay, that's good to know. Well, if you weren't scared off by now, you're never going to be, so that's good. Okay, so anyway, now you can see, here's an example. We have sample X and sample Y. And for each one, the first thing you'll do is calculate the means, okay? So you'll calculate X bar and Y bar. And when you're done with that, then you'll see how this works, okay? So I'll give you a second to write this down if you want to write down these numbers. And then we can carry on with the calculations. And what we're about to see here is exactly what Excel was doing for us. In fact, what I think we're going to do is when we're done here, we'll go back into Excel and actually do the calculations the long way. In other words, not just rely on what you're seeing here. I'll move it over here somewhere. Oh, sorry. Let's go back to what you were doing. Now, in this case, you want to leave them in this order. In other words, don't mess around with the order here. We're looking for the connections between these values. So don't change the sequencing. Leave them the way they are. If you shuffle them around, you'll get a very different result than if you have them in this particular order. All right. Now, we already know how to calculate the means. X bar is the sum of the x's divided by 5, which is 1. Okay. All right. And of course, you can see you're literally just adding up all the elements before you divide by the sample size of 5. And then for y, you do the exact same thing. Add them up, divide by 5, and you have 3. So make a note of that somewhere. X bar is 1 and Y bar is 3. So then we have to go through the list one pair at a time. All right, so we start with, now, okay, so this is X1, this is X bar, this is Y1, and this is Y bar. This is X2, and this is X bar. This is Y2, and this is Y bar. And it goes on and on and on. They're all the same, all the way down to 5. I'll write these in here This is x5 minus x bar. This is y5 minus y bar. So in other words, you're not squaring anything. You're multiplying them one pair at a time. Then you add them up, and then you divide by 4. Okay, so I'm going to leave it there for a minute so you can see. Now, you know, probably what you should do, I jumped ahead here, but what you might want to think about doing is solve for each of these individually before you get down to this point. But remember, you have to be careful with these. It's so easy to make mistakes. Now here, of course, n equals 5, therefore n minus 1 equals 4. And then when you divide by 4, you can see at the bottom, the covariance for that case is -1. So the covariance is negative, which implies the two variables tend to move in opposite directions. The key word there being tend. Not always, of course. Now, there's just one little problem here. Is that a strong relationship? -1. We know that it's negative, but we don't know how strong that connection is between the two variables. Now, this is one of the real problems with the covariance measure. What am I referring to here? Well, I'll mention it on the slide here somewhere. The covariance measure has no upper or lower limits. In other words, -1 might be a very large number and it might be a tiny number. We don't know. We have nothing to compare it with. As a matter of fact, if you look back at my spreadsheet, look what happened here. The first covariance was 169. Then we have -49, -2.9. Who knows what that means? We can tell what the sign is, but the actual magnitude is very difficult to interpret. Well, I'm giving you a hint here. It turns out this is why we usually prefer to use the correlation coefficient, because it doesn't have this problem, as we'll see in a bit. Okay, now, before we go any further, I'm going to show you the equivalent version for calculating a population covariance. And you'll see there's a few important differences. I'm going to save one of them as a surprise. Okay, so let's take a look at how you would calculate the population covariance. Now, you notice how the sigma replaces S, because this is in fact a population. In addition, we have mu now, but look at now, this one suddenly has a subscript. We didn't have this before because we only had the one population. Here we have to know how to tell them apart. So this is the mean of population X. And this is the mean of population Y. So the subscripts are now being used because we need a way of telling them apart. The X's and the Y's are self-explanatory. Here we have the population. Now, this is the common population size for X and Y. Again, they have to be the same. And look, just like with the variance, we're dividing by n instead of n-1. That hasn't changed. Okay, between the sample and the covariant population covariances, the sample version we divide by n-1, and here it's n. All right, so we're not going to do a separate example for this one. What we are going to do is jump ahead and look at the correlation coefficient. We're going to see how it's related to the covariance, and we're going to look at its properties. Okay, correlation is closely related to covariance. Now, the beauty of correlation, though, is that the range of possible values is between -1 and +1. All of a sudden, we have an upper and lower limit, which makes it a lot easier to interpret than the covariance. For example, 0.9 is a very strong positive correlation. 0.2 is a very weak positive correlation. Okay, so in other words, you not only now know the sign, you know the magnitude. And that is very, very helpful. So most of the time, you'll see that we end up using the correlation coefficient. One more thing I wanted to mention here. I'm going to throw it in right now. In addition, correlation has no units. Covariance is affected by the units in which it is measured. That's important too. I'll tell you why. Imagine that we're looking at temperatures. Actually, you know what? Let me add this as a separate slide here. This is awfully important. For example, if our data consists of temperatures in Fahrenheit, the covariance will be different than if our data is measured in Celsius. In other words, if we use temperatures in Celsius, the covariance that we get from that data set will be different from the same data set where everything is expressed as Fahrenheit. And that's a very awkward thing to deal with. So the correlation coefficient has two major improvements over covariance. Number one, the fact that it has an upper and lower limit. Number two, that it is not affected by units. It has no units. It is a pure number. As a covariance, that is not the case. So now, as it turns out, just like when we went from variance to standard deviation, the relationship is very simple. Here's how it works for a sample. The correlation or correlation coefficient, as it's sometimes called, Rxy, equals the sample covariance. And down here, these are actually the standard deviations of the two samples. So this is the sample X standard deviation. This is the sample Y standard deviation. And you notice again, we need subscripts to keep them apart, which never was necessary before. So you're basically just taking the covariance and dividing it out by the product of the two individual standard deviations. And this is why it has all these wonderful properties. This is why it has no units, and this is why it is bounded between negative and +1. Now, you saw how complicated the covariance was to calculate. Now, all of a sudden, you've got to calculate two standard deviations and put them into the denominator. So you can see this is a very complicated process. Yes, it is. Now, so we're going to use this as an example. Our previous example, we found that the covariance was -1, or sample covariance. Now we're going to calculate the correlation coefficient. So what do? We have to now calculate the sample standard deviation for both X and Y. Now, this we've already done. You know how to do this already. So we'll just quickly note that for X, the sample standard deviation turned out to be 2.1213. Okay. And you can see why. We calculated X bar to be 1. Then we went through and we subtracted that 1 from all the elements in X. We squared them, add them up, divided by 4. And then at the end, we take the square root. Then we'll do the same thing for Y. All right. And we went through and we already calculated the Y bar is 3. Now we go through the entire set of values of Y. In each case, we subtract 3, we square the result, and we divide by 4 before taking the square root. This one is very similar. It's approximately 2.2361. So now what we have to do to calculate our sample correlation coefficient is take the sample covariance and divide by these two standard deviations. And then we'll have a sense of how negative this relationship really is. All right, are we ready? Here we go. We've got the big surprise awaiting for us, the actual value of this correlation coefficient. Okay, after all that work, it ends up being approximately -0.21. So in other words, the thing is you can have many different negative relationships. Let me just show you, like, for example, this one is going to look something like this. It's negative, but it's not a terribly, terribly strong connection. Whereas if you had something like this, the points are really close to that line on average. This could be more like -0.9. Okay, in other words, we now have not just the direction of this relationship, but we have the magnitude. So it's a relatively weak negative connection or relationship between these variables. And that's important information. It could help us decide if these are stocks we're looking at, it could help us decide whether or not to put them in our portfolio. So this is really important. Now, I do want to show you the equivalent formula for a population. It's all Greek letters, as you can imagine. There's a new one hiding in there, though, that you may have never seen before. Okay, so if you're ready, we'll take a look. Oh, so you can see the sigmas replace the s's. What is this thing? This is a Greek letter. And just for the fun of it, we're going to do a poll. I like polls. I'm going to try a new poll here. Here we go. All right. So the one I just showed you, we're going to have multiple choices. It could be let's try one of those 4. All right. Here we go. Well, I'm happy to tell you that most of you got the right answer. It is, in fact, the Greek letter rho. So from now on, when you see that letter, this is going to represent correlation. This is one of those letters that's always used for the same thing. Okay, like pi. Whenever you see pi, you know what it means. It's 3.141, whatever. Same thing is true with correlation. We almost always use correlation rho to represent correlation. So that's something you'll run into again in the future, especially if you decide to major in finance or economics. You'll see this quite regularly, especially in portfolio theory. There's a lot of discussion about the correlation coefficient because it helps to explain how well diversified our portfolio is. But anyway, so sadly enough, I don't know how this keeps happening. We seem to be running low on time. Now, this chapter is essentially finished, but I would like to go back to the spreadsheet and work on it a little more just to show you a few more details about how these numbers were derived. And then, wow, the timing is perfect. This is the end of chapter 3. It's so perfect. What we have to do tomorrow is chapter 5. Let's see if we can give you a quick preview of it. Chapter 5 is our introduction to what's called probability theory. Probability theory is very different than what we've done here. It is more theoretical based. So the math will be a little less time consuming, shall we say, but the concepts themselves are more, let's say, advanced. So it'll be a very different type of chapter, but both of these are necessary for everything that follows. So this is the foundation of what comes next. So what you should probably do between now and tomorrow is, continue reading this chapter 3, make sure you understand it and you can reproduce all these results that we've had with your calculator, I mean. And then if you have time, start to take a look at chapter 5 so you'll have an idea of what's coming up. Okay, so it doesn't catch you by surprise, shall we say. All right. So sadly enough, we have to knock it off for today. I know it always seems like we just got started when it's time to stop, but that's just the way it is, So, all right, I'll see you. Unless there's any last minute questions, I'll see you all tomorrow.
Have a good one, Professor.
All right, see you tomorrow.
Have a good one.
All right, bye.